iPad. All right, here was the worksheet. So this is the one you did for bonus. It says classify each as acid-base redox, and then you can do synthesis, decomposition. Synthesis is also, the other word for that is combination, remember. Sorry, let me get the chat up in case people type as I'm talking. Okay, now the one thing, somebody mentioned this 8 a.m. I didn't recognize or realize. It doesn't have precipitation anywhere on here. And there are indeed some reactions that are precipitation reactions. So if you also classify it as precipitation, that's great. Even though maybe in the instructions didn't include that. I'm not gonna go through and balance everything right now, but I am gonna talk about how to recognize what kind of, here was the answer key. I'm gonna post this on Blackboard. I'll probably edit it and add, any reactions that were precipitations, I'll add those and post that by the end of the day. So you can really dig in and check your work if you wanted to. All right, so one of the first reactions we looked at, obviously you can see several of these were listed as something and then also listed as a redox reaction. So like the number 2, synthesis, you got 2 things coming together and it's redox. This one was really, really hard to determine what the oxidation numbers were. Why? Because you have a polyatomic right here, you have ammonium, and within that you have to go in and assign oxidation numbers, and that's hard because things have to add up to +1 and not 0. And then you just see nitrogen doing some really bizarre stuff. But there's a few rules that can help us. I'm not going to put one this complicated on the exam, but I do want to walk through it. So I'm reading the chat. If I said replacement instead of displacement, do you know what yeah, that's fine. But on the exam, type displacement or Blackboard may count you wrong. Okay, what is nitrogen? Remember the rule here. If you read pages 151 and 152 in your textbook, I'm just going to make a note of that. Pages 151 through 152. I begged you guys to read this. Just 2 pages. This is rules on how you assign oxidation numbers. This will be very helpful if you're confused about oxidation numbers still. So you go in, the first element gets the positive oxidation number, the second element gets the negative oxidation number. And remember, they don't always match charges, and that's exactly what's happening here. Nitrogen is a +3. What? That feels weird, but that's what it is. Hydrogen here, this is very weird. What? Why? What is hydrogen doing being a -1? That's what's happening here. In HCl, hydrogen is a +1. Why is hydrogen 2 different things? Welcome to the world of chemistry. Chlorine is a -1, okay? What's happening on the product side? Chlorine is still a -1. Ammonium, what is the charge on ammonium? Ammonium is a polyatomic. You guys remember? I guarantee you like 80% of the class have not memorized their polyatomics. But some of you have, or you have the chart. Yeah, it's a +1. So here's what this means. The oxidation number on nitrogen plus the oxidation number, the sum of the oxidation numbers on hydrogen, because there's 4 hydrogens in ammonium, that has to add up to +1, not 0, because it's a polyatomic with a charge overall. Okay, again, this is why there's so many different layers to this one. This one's really complicated. So here what you see, if it's going to add up to a +1, you've got a +5 on nitrogen and a -1 on hydrogen. Okay, so I'm not going to put this one on the exam. I'm not going to put one this complicated on the exam, but I do want to show you how this is redox. You have things changing charges. So people have asked me, how do I know if it's redox? Remember, we defined a redox reaction as one in which elements are giving or receiving electrons and charges are changing. Something's being oxidized, something's being reduced, and they always happen in tandem. You can't just have something being oxidized with nothing being reduced. They always happen together. So what's happening to nitrogen? It's a +3 on the reactant side, it becomes a +5. So is nitrogen oxidized or reduced?
Oxidized?
Yes, thanks, Keegan. It's oxidized. If you're increasing in charge, you're giving away electrons. Remember oil rig? You guys remember oil rig? Oxidation is the loss of electrons. Reduction is the gain of electrons. Okay, if you're gaining electrons, you're losing charge. You're reducing your charge because electrons are negatively charged. Hydrogen, okay, these hydrogens match these hydrogens, right? They're all -1. But this hydrogen is a +1, and on the product side, we see that all the hydrogens are -1. So hydrogen is going from a +1 to a -1. At least one of them is. So that one's being reduced. Again, if you're like, oh my gosh, this is so hard. Yeah, this is probably one of the hardest redox that I've looked at in a while, okay? So fortunately, on this worksheet, it did not ask you to identify what is oxidized and what is reduced. It just asks you to label if it's redox. So if you can tell something's changing charges, it's much, much easier with problems like this. I'm just going to go through and circle problems that I automatically see are redox. Why? How do I know these things? When you have elements that are by themselves, I'm going to highlight anytime I see an element by itself, I know, and then it's in a compound on the other side, I know this is a redox reaction. Okay. Why? Because it has an oxidation number of what? When something by itself has oxidation number of what? Zero. And when it's in a compound, its oxidation number is not 0. That's a red flag. Oh, something's changing charges. So if I ask you to just classify without asking you what's oxidized, what's reduced, that should really simplify how you identify a redox reaction. Okay. Is this helping at all? Okay. I hope so. They're hard. Let's talk about which reactions. Did anybody get any of these as a precipitation reaction? Anybody label these precipitation? Number 10, Grayson said number 10. Let's look at that. Number 10 is right here. You got sodium hydroxide and you got copper sulfate. Gleanna, is the bonus going to be given on correction or completion? That's a great question. There's a lot of problems here. So probably I'm just going to do completion. Okay, you're welcome. Could we go over precipitation? Yeah, Bradley, that's what we're about to do. So if we didn't label them precipitates, are we not going to? No. If you just completed the worksheet, if you did, if you gave me your best attempt, then you're going to get the bonus points, okay? You're welcome. You're welcome. It would take me forever and a year to grade on accuracy. But I hope you tried to be accurate, okay? All right, 10 is precipitation. How do I know? Let's look at these products. Remember, precipitation is you have two substances that are aqueous on the reactant side, and then one of them forms a solid on the product side. So sodium sulfate, copper hydroxide. Which one of these would form a precipitate? We need the solubility chart, which, by the way, by the end of today, I've got a lot of things to do today. I'm going to post the resources page for exam 2. What's going to be on your resources page? Well, a periodic table like normal, and then a lot of charts. Okay, your solubility chart, your molecular geometry chart. You guys remember geometry, tetrahedrals, all that? That'll be on there. Electronegativity chart. That'll be on there. I'm sure I'm forgetting one, but you'll have a lot of charts like that. So if you want to see what's on there, you can get on tomorrow morning or tomorrow sometime and just look over that so that you know you'll have those things quick print it off if you want. I don't care. I like to print it off and then write all over my periodic table so that I know I got my charges and things listed. That helps me. But let's go to the solubility chart right now. So we got sodium sulfate. Is this going to be aqueous? Is it going to be soluble, or is it going to form a precipitate? What do y'all think? Do you see sodium or sulfate anywhere on here? Remember, if it's, people are like, well, how do I read this again? I forgot. Here's how you read it. If it's on the chart, it is soluble. If it's on the chart, it's soluble. If it's not on the chart, it's not soluble. It will form a precipitate. The tricky parts are your exceptions. Okay, you got this whole box down here. These are exceptions. These form precipitates. If it's an exception, it forms a precipitate. You abbreviate that S. If it's soluble, You abbreviate that AQ. All right. So I saw in the chat, a lot of people said right here, sodium sulfate is going to be aqueous. And they are correct because both sodium and sulfate are on the chart. Copper hydroxide, Cu and OH. Neither one of those are on the chart. So that's why we had some people say they classified this as a precipitation reaction, and they're correct. Because you get a solid. Question, if something forms a precipitate, so something that forms a precipitate, if one of the things is on the chart and one isn't. Claire, yeah, if no, Claire, if where's my chart? It went away from it. Right here. If just one piece is on the chart, like your cation, if your cation, so let's say we have NH420. Ammonium's on the chart, oxygen's not. But that forms a precipitate because anything with ammonium in it, what did I just say? That is soluble, does not form a precipitate. I'm sorry, I'm getting my words confused. That's soluble. Even though oxygen's not on the chart, ammonium is. If just one portion, cation or anion's on the chart, it's soluble. Okay, unless it's a exception. Another question from the chart. Does it have to be aqueous and solid to form a precipitate? Bradley, you're talking about the two products. Usually you get one product that is aqueous and just one that forms a precipitate. It's very, very rare that you get both things that form a precipitate. So yeah, it works out where one's aqueous and one's a solid. Okay, all good questions. I think there was another one. Let me see if I can identify another one. Number 5, barium sulfate. Barium sulfate is an exception. So that one forms a solid, okay? So that one is precipitate as well, number 5, okay? AlCl3 is aqueous. Okay, any other questions on this? Again, I'm not taking time to really dive into everything, but I wanted to walk over a couple of things that I think are helpful because I think redox and that solubility chart are, well, none of this is easy, right? But it's really complex. So another question, how can you tell when something forms a solid? Anybody want to chime in on that? I'd love to kind of hear it from students' words. Maybe y'all can help explain in a way that helps each other.
If it's not on the solubility chart.
Okay, so if it's not on the solubility chart or if it's an exception, it forms a precipitate, which is a solid. Okay, let's jump over to the lecture slides. So go to your mole mass relationship slides. I hope that helped answer your question, Claire. If it did not, shoot me an email and we'll talk further about this. So this is the end of chapter 6. Remember we talked about mole ratios. And this little diagram page is my favorite. Some of y'all maybe hate it. I was getting lots of questions this morning. How do you read this thing? I don't know how to use these diagrams. If this is not helpful to you, you don't have to use it. I just wanted to make it available as a resource because it usually helps me. But we're going to use that, and we're actually going to work this problem. This is a 3-step problem, but I think it's challenging for several reasons. You have to write out your balanced chemical reaction. You have to calculate your own molar masses. There's 2 questions on this. We're actually just going to do one of the 2 questions. So let's read this problem. It says you need to make 100 grams of calcium oxalate. What in the world is oxalate? Well, it's drawn out here for us. The picture is not so much what we care about. We need to write a formula for oxalate. Okay, it's kind of like a polyatomic. You got multiple atoms. It's an ion because it has a charge overall. So how would you write the formula for oxalate?
Would you do a C2O4?
That's perfect. I don't know who said that, but good job. C2O4, and it's got a -2 charge. So C2, we're going to come back to this. And it says calcium chloride. So here's where we're gonna read the sentence and write our balanced chemical reaction from the sentence. Calcium chloride mixed with sodium oxalate reacts to make calcium oxalate and sodium chloride. That's a lot of words. Okay, which ones are our reactants? Let's label those. Calcium chloride, here's a reactant. And sodium oxalate, that's our other reactant. So let's write out the formulas for our reactants. Calcium chloride. Calcium chloride. Some people, I spent a lot of time on my office hours today helping people write out formulas, which goes back to chapter 3. That's where we learn to write formulas for ionic compounds. What you need is a periodic table. Actually, I have one. I have one right down here. Need a periodic table. Calcium's main group 2. I like to scribble all over my periodic tables. I like to write in the charges for all the main groups. Okay, so these are charged. So calcium, main group 2, so it's a +2. Chloride's main group 7, so it's a -1. That's literally what I do when I write these things out. So we're just going to write CaCl2, right? Because the main rule when writing compounds, ionic compounds, is everything's got to add up to 0, charge neutral between your ions, cations, and anions. Okay, sodium oxalate. Who wants to write the formula for that? Sodium, where's sodium? Right here, main group 1. It's got a +1 charge. So oxalate, we said was C2O4, the -2 charge. How many sodiums and how many oxalates? So Haley says Na2C2O. I think she meant to put a 4. She put a $sign. So, but she got it right. Na2C2O4. There you go. So that's the formula for sodium oxalate. Okay. And now we're going to write our problems. It says reacts to make calcium oxalate and sodium. So this is a double displacement reaction. So write the formula for calcium oxalate. You got a +2 cation and a -2 polyatomic anion. And you got sodium chloride. That's the easy one, right? Sodium chloride. So what would calcium oxalate look like? You should write calcium, Ca. It's +2. Oxalate is the C2O4. It's a -2, so you just need 1 each. If you needed more than 1 oxalate for any reason, you'd have to put parentheses, right? Because it's a polyatomic. And then we got sodium chloride, NaCl. Okay, so that's one of the hard parts is over, but now we got to balance it. What coefficient should I put where to balance this thing? Tyler, coming in clutch. 1, 1, 1, 2. Okay, 2 right there. And then we're done. That wasn't too bad. If it helps you, remember, you can always take inventory. Calcium, we got chlorine, we got sodium, we got oxalate. You got oxalate on both sides, so just treat that, oh, that's a 4. Treat that as a unit. And then you take inventory. I got 1 and I got 1. Chlorides, we saw that we had 2. And when we put the coefficient over on the product side, we got 2. Same for sodium, 2. And now that coefficient gives us 2 on the product side. Oxalate, 1 and 1, okay? All right, so that's one hard part over. Now let's actually read the question. We haven't even finished reading the problem. In blue, and try again, in blue, how many grams of sodium oxalate and how many grams of calcium chloride do you need? There's 2 questions there. We're just gonna answer the first part, which is how many grams of sodium oxalate do you need to make how much? 100 grams of calcium oxalate. This is a 3-part problem. How do I know that? I am given the mass of something, 100 grams of calcium oxalate in that first sentence, and my question is asking for the mass of something else. Given the mass of one thing, my question is asking for the mass of something else. So that's like my mass A to mass B conversion. That's this right up here. Okay, we're given 100 grams starting out of our calcium oxalate. So we can call that substance A if we want. And we're asked how much sodium oxalate, Na2C2O4. Okay, how many grams of that? So that's why it's a 3-part problem. The arrow here says both. Both what? What does it mean both? You're going to use both mole ratios and molar masses to complete the problem. And I'll tell you this, the bones of the problem are always the same. Okay, you're always going to have the 3 steps. Step 1 is always going to be the molar mass of your first substance. You're going to plug that in and convert. Step number 2 is always that you plug in the mole ratio between your two substances. So hopefully you balanced it right. Step 3 is, again, always the same. Use the molar mass of your second substance. So we're going to have to calculate those, calcium oxalate and sodium oxalate. So if we're going to use molar masses, let's go ahead and do that. Right down here, I'm going to kind of zoom in on this corner. We have calcium oxalate, CaC2O4. Somebody calculate the molar mass of that while I write everything out. You got calcium, carbon, and you got oxygen. And I have 1 calcium, so you do 1 times, we'll go with the periodic table in just a second. Carbon, I've got 2 carbons, so I'll do 2 times the mass of my carbons. Oxygen, I got 4, so I'll do 4 times the mass of oxygen. Okay. And then we also have sodium, Na2C2O4. We're going to calculate the molar mass of this one. So we got sodium, 2 times the mass of sodium, carbon, 2 times the mass of the carbons, oxygen, 4 times the mass of the oxygens. All right, so we need a periodic table, which I think is the slide below us. Calcium is, we have it circled, 40.078. 40.078. Carbon, we've written 100 times. You should have this number memorized. If I woke you up in a dead sleep and said, what's the mass of carbon? You'd say 12.011. Oxygen, we just use 16, right? So Gliana went ahead and calculated this for us. When you multiply all these out and then add them all up, she says 128.1 grams of CaC2O4 and 1 mole, okay? And then the sodium oxalate. Sodium, if you look at the periodic table, I'll come back to that in a second. Sodium is 22.98977. So that's another one, just like oxygen, I just round to 23.0. Okay, so it should kind of work out like this. And then what is it for Gliana? Got 134. No decimals, 134 exactly. 0.022. Okay. Anybody just totally lost and confused so far? Give me some emojis. How are y'all doing? Bradley says a little bit. I'm seeing a few. Well, I'm seeing some thumbs up. Okay, good. If you're lost and confused, let's recap what we've done so far. We read the problem and we wrote out formulas first. Then we balanced our chemical equation. Then we calculated molar masses because we recognize this is a 3-step problem. We got to use molar mass. Okay. In the chat, why did we find the molar mass of that formula? Of these two formulas, calcium and sodium, because from our question, Bradley, the blue, underline blue part, I'm going to underline it with the black pen. How many grams of sodium oxalate? So this is one substance that we have to get a molar mass for because the question's asking how many grams. It says you need to make 100 grams of calcium oxalate. So see, these two substances are the ones we're interested in for this question. So that's why we had to get the molar masses of that, because these are the two involved in our 3-step problem. So that is sodium oxalate and calcium oxalate. Okay, does that help, Bradley? Okay. All right, now we're going to work the problem. So we're going to start with 100 grams. Well, it says, I think it would be beneficial if we did another example, maybe in the last 20 minutes for review. Well, we got to play Kahoot. I want to give another bonus point opportunity. But if you want more review, join me tomorrow at 10 or watch the recording of that and I can do another one there. Okay, so 100 And the lab. That's why we did a lot of this on the lab. Okay, 100 grams of CaC2O4. Step number 1, plug in the molar mass. So we got it right here, highlighted in blue. Oh gosh. How many times? If I had $1 for every time I did that. 7, so I want to put 128.1 grams on the bottom. And I like to write in my substance C2O4 for every 1 mole. CaC2O4. Grams, what happens to grams? They cancel. Okay, we're going to keep going. Plug in mole ratio. So step number 2 is always the mole ratio. What's the mole ratio between calcium oxalate, sodium oxalate? You're looking at the coefficients in your balance reaction, and I'm seeing this right here, 1 to 1. That's right. So for every 1 mole, now this is really important that you don't get this mixed up. Even though it's 1 to 1 here, obviously dividing and multiplying by 1 is not going to change your answer. So people tend to think, oh, I can skip the step. No, you cannot. The units matter. And if you leave this out, I will not give you points. That's very mean, isn't it? But it's not mean. Okay. And the reason I had to put calcium oxalate on bottom is because look, I got it on top and bottom. It's got to cancel. I'm trying to get things in terms of sodium oxalate. My question says how many grams of sodium oxalate. So I have to cancel moles. So it matters which one I put on top and bottom. You can't put the calcium oxalate on top. It's got to go on bottom. And then I'm running out of room here, but we've got to put the molar mass in the last step. I'll zoom back out in a second. I want to, is this bad to squeeze it all in? Molar mass, step number 3 of sodium oxalate. So for every 1 mole of the sodium oxalate, it was how many grams? We had it right down here. 134.02 grams. Zoom back in. And notice, lastly, again, moles of sodium oxalate cancel out. So now we're going to be left with grams. So anybody want to calculate this for us? 100 divided by 128.1 times 1 divided by 1 times 134. Then I got 104.6. 104.6. Summer got that as well. Okay, it's confirmed. 104.6 grams. All right. If you just feel really unsure with these problems still, you are going to have one of these. It will be a file response. And I want to see you show all your work. I want to see you calculate the molar masses. I want to see you show the 3 steps, plugging things in, crossing out units to get full points. Remember, I get partial credit. So if you get 90% of it right and you just get the wrong answer, I'm going to give you 90% of the points. Bradley said, I need a 2-step problem if possible. Well, maybe I'll put a 2-step on the exam, but you're also going to have a 3-step. I'm not doing a 3-step. Okay, that'll be 1 file response. The other file response question on the exam will be Lewis structures. Okay, Lewis structures. You'll have to draw a couple of those out. So let's move on to the actual review stuff. Oh, goodness. I forgot to erase. Don't look. This was a mess. I felt so bad for my 8 a.m. students. This is a totally incorrect. Don't spend your time on this one. I need to rewrite that. But we're going to practice drawing Lewis structures, and then we'll look at some molecular geometry stuff. And then based on time, we'll see how far we can go, because we got to save about 20 minutes again at the end to do Kahoot. Okay. We're all over the place. I told you it's going to be kind of sporadic. We're just continuing review. So we're going to review chapters 4, 5, and 6. Before we really jump into these questions with the review, last time I had some people say it was pretty helpful. We made a list, right, for exam 1. I said, what all is going to be on exam 1 from chapters 1, 2, and 3? Let's make a list. So grab a sheet of paper. I'm going to give you about a minute and a half. Try to name 10 different concepts or topics from chapters 4, 5, and 6. Try to name about 10, see if you can get 9 or 10 Chapter 4 had a lot in it. Okay. And just go ahead, start writing down different topics from chapters 4, 5, and 6. If you can put away your notes and do that, great. If you want to look through your notes, that's going to take more time. And then we'll come up with a list together. Think back on chapters 4. What did we do? I'll give you one. That was the chapter we drew Lewis structures. All right, we've been going about a minute, so I'm going to give you about 25, 30 more seconds. And then we'll see as a class what we can come up with. All right, no matter how many you got, I'm sure you got a few at least. It's okay if you didn't get all 10. Throw some at me in the chat. What do you guys got? What topics from 4, 5, and 6? Okay, balancing chemical reactions, classifying chemical reactions. Those were all chapter 5. Summer put polarity, Haley, mole relations, Danielle, Vesper model, which is, yes, molecular geometry. All good stuff. Okay, naming chemical compounds. Yes, Claire, the binary compounds. Diatomics, writing chemical formulas, electronegativity, Avogadro's number. Yep. Okay, so this is what we came up with this morning. And I'll scroll back down. Actually, let me turn it sideways. Maybe you can see it all at once. Okay. I know it's a little bit smaller. We said chapter 4. So screenshot this if you want. Chapter 4, we said the big hitters were covalent bonds, molecular geometry, Lewis structures, naming binary compounds, remembering your diatomics. Okay, polar bonds, polar molecules. Those are pretty interesting, pretty difficult sometimes. Balancing in chapter 5, balancing and classifying reactions. And yes, Danielle brings up a good point in the chat. Lewis structures, you have your regular formulas and then you have your condensed structures. Okay, so remember the different nuances with condensed structures and how to draw those out. And parentheses, what happens if you have parentheses in those. Yeah, chapter 5, really balancing and classifying. There's a lot under classifying, right? But it's all under that umbrella of learning to classify reactions. Okay, chapter 6, we said we identify what a mole was, Avogadro's number, how to calculate molar mass, how to pull out mole-to-mole ratios from chemical reactions. And then I just put 3-part problems because those kind of seem like their own thing. Electronegativity is a topic or a concept. I absolutely agree. Somebody put that in the chat, hey, Heaven, that falls under polarity, okay? Learning how to classify bonds as polar, nonpolar, or ionic based on their electronegativity differences. Okay, drawing in the dipoles. We did a really, really good practice on that on the office hours. I'm actually going to post the recording from my office hours today because I had somebody request that. Bradley, yes, we can. Really quick, just because you asked. Drawing in a dipole. When do you know to draw in a dipole on a bond or on a molecule? Can anybody answer that for me? When do we draw in a dipole?
When it's polar?
When it's polar and you have the electrons in the bond are not shared evenly. Okay, so for example, you got HCl, molecule of HCl. Okay, Claire, the The symmetrical thing is a little more nuanced, and I can address that, but hold on, let me finish this first. This is the slide I'm looking for. Okay, we worked this problem from the textbook, by the way. This was problem 4.76. I encourage you to go look at it and work it. We worked it on the office hour. But you gotta look at this electronegativity chart. And here's what I see. We got hydrogen and chlorine. And hydrogen has an electronegativity value of 2.1. Chlorine is right here, 3.0. So I'm gonna slide back over to my note and we're gonna calculate the difference. Remember, you do 3.0 minus 2.1 and you get a difference of 0.9. This is a polar bond. So now I'm going to ask you which element is more electronegative, which one is less electronegative. Yes, Kiara, this chart will be on the reference sheet. Electronegativity chart. So hydrogen is the less electronegative element. So you put the partial positive on hydrogen. Chlorine is the more electronegative element. You put the partial negative on chlorine. The closer an element is to fluorine, the more electronegative it is. Now let's draw the dipole in. It always points towards the negative side. And you put a little cross on it at the partial positive region, okay? Water is another example. Okay, oxygen is the more electron. I'm not going to take the time to do the electronegativity difference, but when you do, you find oxygen is the more electronegative element. Hydrogens are the partial positives. You can draw two dipoles in here because you'd have two bonds. You could draw a dipole in for every bond that's polar. So I'm going to draw it pointing towards the oxygens. Now, some people would say, oh, these cancel out. No, they don't. They only cancel when they're pointing opposite directions. So if you have dipoles that you draw in like this, pointing left and right, and the arrows are pointing opposite directions, sure, these would cancel. But on water, both of them are pointing the same direction, so they don't cancel. Okay, so that's a little bit of a review on polar bonds and molecules. So do you subtract once or twice? Bradley, you only have one kind of bond on oxygen and water, or in the water molecule. You just have an oxygen-hydrogen bond. So just calculate it one time. It's the same kind of bond. Now, if you have different bonds, okay, if I got CH3, Cl, I got two kinds of bonds there. So yeah, I got to calculate the electronegativity difference for a carbon-hydrogen bond and a carbon-chlorine bond. But you don't have to do it 4 times because carbon-hydrogen is going to be the same number every time, right? Okay. I hope that helps. All great questions. Claire, when it's symmetrical, you could end up with a situation like this where your dipoles cancel. Okay? That's like a molecule of CO2. All right, let's go back over to all good questions. Thank you. I really appreciate you guys asking so many questions. I think that's a good thing. All right, let's start with some review. Here we go. Molecular compounds, covalently bonded compounds, usually form between what? 2 metals, nonmetals, or a metal and a nonmetal. What do you think, A, B, or C? You can just type it in the chat. Keegan says C. Kishan says C. Summer disagrees. Summer says B, 2 nonmetals. Okay, ionic compounds form between a metal and a nonmetal. I'm asking you about covalently bonded compounds. These, if you remember, all the way back, the very first slide in chapter 4, I think, one of the first 2. Chapter 4 is huge. Okay, we said, where is it? 2 nonmetals. Boom. Okay, so B is the correct answer. Right there. Again, I told you if I had $1 for every time I meant to do highlighter. All right, element X have 5 valence electrons. How many bonds will it form in a Lewis structure? What rule did we write down in class to use for questions like these? I want to say this was the video lecture because we had the snow day. So if you remember from that video lecture, nitrogen or phosphorus is a good example here. If you got 5 valence electrons, I'm seeing in the chat, everybody's saying 3 bonds. And that is correct, 3 bonds. Okay, if you've got 5 valence electrons, you want to gain 3 more to get your octet. And the octet rule does play into effect, but I kind of had a motto. Every time you share an electron, you gain an electron. So the number of electrons that an atom needs to get an octet is equal to the number of bonds it will form. The number of electrons an atom needs to get an octet is equal to the number of electrons, or sorry, the number of bonds it will form in a compound. Okay. Next one, which of the following is or are not diatomic molecules in nature? So there may be more than one correct answer here. What do y'all think? Just type the answers in the chat. Okay, Maddie says, so I'm seeing a lot of D or the phosphorus one. I'm seeing a lot of A and D. Okay, so far the votes are A and D, sulfur and phosphorus, and that is correct. Neither one of these exist naturally as diatomics, but oxygen and fluorine and hydrogen do. That's correct, Grayson. Okay, next one. Name 3 elements that are exceptions to the octet rule. No, we're not doing that. I'm not gonna put exceptions on the exam. We're gonna skip that. All right, let's draw a Lewis structure, and let's not draw it for number 2. That was a disaster this morning. I was so embarrassed. All right, let's just do, which one do you want to do? 1, 3, or 4? First one I see in the chat, we'll draw. Okay, I saw 1 first. Okay, C3H7OF. You got 3 carbons, and remember those always make good central atoms. So bond your carbons together. Then we got hydrogen. So usually hydrogens make really good. We just throw them on our carbons. So start bonding like this, but we need to leave a space. That's 4, 5, 6, 7 hydrogens, and we got a space on this last carbon for the oxygen. I cannot put fluorine here because then I'm at a dead end. Now I don't have a spot for an oxygen bond because hydrogen and halogens, they cannot have more than 1 bond. Okay, so we can't do that. But we can put the oxygen there and then throw the fluorine on the end of that. Just like that. You could do it several ways. You could put the fluorine over here if you wanted. I don't care where the fluorine goes. There's so many different correct structures. And then you could put the hydrogen down here if you wanted. Okay, all of these would be accepted as correct. All right. CH3COH, that was another one y'all voted on. So real quick, you got a CH3 group. This reads more like a condensed structure. And then you got carbon. You know what? There's a typo on this too. This has got to be in parentheses or else this molecule does not work. That's got to be in parentheses. So pretend I had parentheses there. All right, so now that we have parentheses, what does that mean? That means that is branched off of this carbon right here. And it's got to be double bonded because oxygen has to have 2 bonds, 2 lone pairs. Then you got an OH group, which is also branched off of this carbon. So up or down or to the side, but it's got to look like this. The O and the H, these things are together. So they've got to be bonded together. You cannot separate and put the hydrogen on the carbon directly as well. It's got to be O and then H. Okay. And then you go back and double check. All your carbons have 4 bonds. Oxygen, 2 bonds, 2 lone pairs. Hydrogen's 1 bond. Okay, remember, never put a lone pair on carbon. Why did the first oxygen get a double bond? Okay, because oxygen, the rule for oxygen, based on its valence electrons in the octet rule, it's got to have 2 bonds and 2 lone pairs. And when you look at an oxygen in parentheses right here and how it's bonded to this carbon, that means that carbon is the only atom the oxygen's bonded to. So it's got to have both bonds to carbon, and then it gets 2 lone pairs. Okay, so that's why it has to be a double bond right here, because there's no other atoms this oxygen's bonded to. So both bonds go to the carbon. Does that help? Okay, let's do a little molecular geometry, and then we're going to be coming up on time to switch over to Kahoot in just a minute. All right, which of the following molecules would have trigonal planar geometry? Trigonal planar geometry. So this morning I did not have time to jump over to the table, but I bet I have time to scroll to it right now. The table that you need to help answer questions like this will be on your resources page, we're talking about the Vesper model right here. You guys remember this one, I bet. This is the table. So let's go back to our problem and let's see which one this matches. Remember how to count charge clouds? Charge clouds, you count bonds or bonded atoms as a charge cloud, and then you count lone pairs as a charge cloud as well. So here we are. Drawing the Lewis structures for these will help you. If you're quick at Lewis structures, you just sketch them out. This is a single bond, sorry. And Br. And then, of course, you got all the lone pairs on the bromines, but we don't count the lone pairs on bromine because we're trying to name carbon. Carbon's our central atom. We don't count lone pairs on exterior atoms. Here, carbon has no lone pairs. So carbon has 4 single bonds. So what geometry would that correspond to? 4 single bonds, 4 bonds, no lone pairs. That's right. 4 charge clouds, tetrahedral. So that's not trigonal planar. So that's not it. All right, boron. And we got 3 bonds. Boron does not have any lone pairs. This one is an exception to the octet rule. It's only got 3 electrons it can share. So once it's got 3 bonds, it's done. So what kind of geometry would this be? How many charge clouds? I see 3 bonds, no lone pairs. 3 bonds, no lone pairs. What does that correspond to? 3 bonds, no lone pairs. You're looking at these first 2 columns. Keegan says trigonal, Tyler trigonal plus, right. This one right there. Okay, so that fits. So that one answers our question. This boron is trigonal planar. OF2, what does that look like? You got an oxygen, fluorine on one side, fluorine on the other. This oxygen has 2 lone pairs. Remember, oxygen, 2 bonds, 2 lone pairs. That's the rules for oxygen. 2 bonds, 2 lone pairs. So 2 bonds, 2 lone pairs. What would that be? If we go back to the table, it's 4 charge clouds. Sterling says bent. Keegan bent. Tyler, okay. Yep, that one's bent. PCl3 looks a whole lot like BF3, right? Maybe that's trigonal planar. What do y'all think? Is this the structure?
Yes.
No, we're not done. What are we missing?
Okay.
Sorry, we got one
Lone
thing.
pairs?
There we go. Thanks, Bradley. Got a lone pair on that phosphorus. Okay, it's main group 5, so it's got 5 valence. So you got 1, 2, 3 in the bonds, 1 in each bond, and you got a lone pair. So is this going to be trigonal planar? If it just had 3 bonds, it could be, but that lone pair makes this what? There's 4 charge clouds here. When you go look at the chart, it's pyramidal. And then ASF5, this one's crazy. This one exceeds the octet. Got fluorines here. So this one's definitely not trigonal planar. We're not actually going to go into that one, but it's not trigonal planar. Okay. I'm not going to have anything like that on the exam, though. I'm not going to say what's the geometry of that. Okay, there's more questions here. Again, I'm sorry, I don't want to overwhelm you, but I always like to have more review material than possible. So tomorrow at 10, I'm gonna go through more of this and I'll answer questions. And let's continue the review though, but this time for an opportunity for points. Y'all want that, right? All right, I'm gonna stop sharing. Give some people another second to finish drawing these. Go ahead and grab your cell phone, or you can do it on your computer as well, but you need to go to kahoot.it. I'll show you the website in just a second if you don't know how to spell that. Kahoot.it, so pull this up. Okay, it's downloading for a second, and then I'll share to my desktop. All right, we're gonna do classic. Okay, it's loading the game. So what you need to do is you should be able to see it tells you right here, join at www.kahoot.it. And we have 62 of you. And when it loads the game pin, okay, right there. Don't y'all love the music? I don't. I actually think it's kind of annoying. So I'm gonna turn it off. All right, so when you get there, it'll prompt you for the game pin. So I see people joining. 449-2858. Oh, we got something in the chat. Thank you, Tyler. Thank you for that comment. Put a creative name if you want to. If you're competitive, you will. All right, we're at 57. Anybody else want to join? I don't see the number going up anymore. Oh, 58. 4 more people. Y'all there? Oh, 61 actually. 2 more people. I'm gonna start it if that number doesn't go up. Here's your chance to join now. All right, here we go. Start. So these are gonna be timed. We got 59 people. And some questions are quick. This first one's quick. I think you got like 10 seconds on the first one. Which element does not naturally exist as a diatomic molecule? All right, 10 seconds. Quickly, quickly. Fluorine, hydrogen, phosphorus, or nitrogen. Okay, I hope you got your answers in. Sorry if that was too quick. Other problems, I promise you'll have more time. So the correct answer is phosphorus. We kind of actually went over that in the review as well. And let's see who's in the lead. I love how it always shows who's in the lead. You do get points if you put your answer in the quickest, by the way. All right, let's go to the next one. Predict one product from a double displacement reaction between the following 2 reactants. Okay, what matters here are the charges. This is hard. You got a minute and a half though. You need to write a product. So this is double displacement, the cation from one and the anion from another. But you got to deduce the charges. Specifically on this nickel here, you should be able to predict the charge on aluminum. I say write out your products and then look at your answer choices. What is the charge on that nickel? How do you figure that out? I spent a lot of time on my office hours helping people. Emmy, yikes. I don't know how to, I don't remember the game pin.
I got back in. We're good.
Oh, you did? Okay, good. You got about 20 seconds. Oh, game pin's in the bottom corner. I probably can't see it because I had my, yeah, Bradley, we're gonna go over this one. There you go, game pin's down there. Boom, okay. Why is this the right answer? I'm glad we're gonna go over this because look at that answer distribution. Wow, okay. Only 16 people picked this. Why is it NIS? Okay, let's talk about this. Nickel and phosphate. What is the charge on phosphate? It's a polyatomic. Y'all should know this one. Phosphate is a polyatomic with what charge? Plus, no, it's polyatomic, so -3. There you go. I think Summer meant -3. It's a -3 charge. You got 2 of them. You see this little subscript 2? That means -2. Or sorry, that means 2 of them. So that's -3 times 2. That's a -6 total of a magnitude of -6 negative charge in nickel phosphate. We're trying to figure out what the charge on nickel is. And that's complicated, the most complicated actually, because it's a transition metal. And sometimes transition metal can carry different charges. So we can't look at this like a main group cation and say, oh, aluminum. I know aluminum's +3. Why? It's in main group 3. We can't do that with nickel. So we've got to figure this out from looking at the anion. So phosphate's a -3. We got 2 of them. That adds up or multiplies out to -6 total. So we've got 3 nickel cations. Remember, one of the rules when you're writing ionic compounds is that the positive and the negative charges add up to 0. So the cation side also has to multiply or add up to +6 because +6 and -6 add up to 0. Where did I get the -6? From the 2 phosphates. So what is the charge on nickel? If I have 3 of them, and across the 3 nickels, they've got to be +6, and they're all the same. What is the charge on nickel? It's a plus. Okay, Summer said +2. Yeah, it's a +2. +2, +2, +2, that gives us +6. So now, when I go write my compound, I know nickel's going to join up with sulfur because it's the other anion. So your options were NiS or Ni2S3. Ni2S3 is not right because there nickel has a +3. NiS is good because nickel has a +2 charge there. The charge does not change for nickel across the, this is not a redox reaction. This is just a double displacement. And so you got nickel sulfide, NiS, 1 each. Because sulfide we know is a -2. It's in main group 6. Bradley said I'm lost. Okay. Bradley, will you shoot me an email? If you're lost on anybody else, I mean, I guarantee you there's a bunch of people lost on this. I'll try to spend some time going over this in the review tomorrow, and that will be recorded. Watch that review. This is chapter 3 stuff. So if I can give you like, okay, what could you do over the next 24 hours to get a question like this? You need to go review a couple of chapter 3 things. We talked about how to write ionic compounds. So some of the slides there, or again, just shoot me out an email and I'll respond to that today, or we join the review tomorrow if you can at 10 a.m. Okay. It's hard for me to talk about this without writing it out, and I don't have a screen. But anyways, let's go on to the next question. But please send me an email or reach out to me if you're lost on this stuff. All right, there we go. Next. What's the mole-to-mole ratio for SiCl4 and HCl in the following reaction? So you got silicon tetrachloride. This is a quick one. You got 30 seconds here. What is the mole-to-mole ratio? You're just looking at the coefficients in the balance reaction. Six seconds, 5, 4, get your answers in, 3, 2. All right, majority of people, landslide, said 1 to 4. That's correct. You got a coefficient of 1 in front of SiCl4. You got a coefficient of 4 in front of HCl. So it's a 1 to 4. You can't simplify that. All right, next. Let Keyshawn, please. Okay, which of the following is a precipitation reaction? You only have 30 seconds here. I give you the abbreviations like AQ and S, so that should make it really, really simple to identify. Seven, 6, 5, 4, 3. All right, landslide, everybody said number 1. That's right. CUS forms a solid, which means it's a precipitate. Good. None of the other reactions had a solid on the product side. Who's in the lead? Allie has the highest answer streak. Good job. Danielle's in the lead. Okay, next. In this redox reaction, what is oxidized? What is reduced? You got it right and move back this way. Okay, so you got a minute and a half here, so don't rush unless you're trying to be first. Some of y'all are just guessing. What is oxidized? What is reduced? Remember oil rig. I see chlorine by itself, sodium bromide, and then I see bromine by itself, and sodium chloride. When something's by itself, remember what kind of oxidation number you give it. Still got 30 seconds. I think most people are done, but that's okay. Still got time to get your answer in. Almost there. Last few people. If you're really not sure, just guess. You'd rather guess and have a chance of getting it right than not answer. Ten seconds. Final few. All right, the answers are, correct answer is D, essentially, or the green. Bromine's oxidized, chlorine's reduced. Okay, so look, bromine over here on the product side, on the reactant side, it's a -1. On the product side, it's a 0. So -1 to 0 is an increase. -1 to 0 is an increase. That's oxidation. 21 people picked the opposite of this. Okay. Chlorine is a 0 starting out, and it is on the product side a -1. So 0 to -1, that's reduction. So chlorine is reduced. Bromine's oxidized. So a lot of people picked similar things, just opposite. Haley says, so gaining or losing is in electrons. So oil rig. Oxidation is the loss of electrons. Okay. When you lose electrons, you're giving away negative charge, so your charge increases. If you're gaining electrons, your charge is decreasing. Does that help, Haley? Okay. What do we got now? Okay, I see you, Danielle. All right, draw the Lewis structure for the following molecule. Name the geometry of the second carbon. CH3, C with an O, and then OH. Is that second carbon tetrahedral, trigonal, planar, pyramidal, or linear? You got plenty of time. Greenlee, what happened? Can you join back in? 15 seconds. Can you go back to Kahoot.it and enter the game pin? It's in the bottom right corner. Or are you just saying you accidentally picked the wrong answer before you're ready? Maybe that was it. All right, trigonal planar. You should Okay, I thought you meant you got kicked out. Should have something that looks like this. Okay, carbon with 3 hydrogens and then a carbon with an oxygen and then an OH group. That second carbon there has 3 charge clouds, 3 bonded atoms, no lone pairs ever on carbon. So that should be trigonal planar. Okay, trigonal planar, that's what that is. So a lot of people pick tetrahedral. Don't assume carbon's tetrahedral, although often it is. There it's trigonal planar. Okay, questions on that before we go to the next one? All right. We're on 6 of 16. I don't know if we're going to finish this because we have a few minutes left. Okay, next. Name the following binary compound, P2O5. So you need prefixes here. What's the prefix for 2 and what's the prefix for 5? And read the answer choices closely. There's 2 that look very similar. All right, 7, 6, 5, 3, 2, 1. Correct answer is diphosphorus pentoxide. Okay, di stands for 2, and then it's phosphorus. The reason why the blue one's not right is because it's not phosphide. You only change the ending of the second element to IDE. All right, so diphosphorus, not phosphide, and then pentoxide, you drop the A when the element name starts with a vowel. So not pentaoxide, just pentoxide. Drop the A if the element name starts with a vowel the way oxygen does. That one, okay, I agree. That one's tricky and technical. But, okay, next. Ashton's running away with it so far. Which of the following bonds is non-polar? One of these should scream non-polar. Five seconds. Okay, should be the carbon-carbon bond. Anytime you have 2 identical elements in a bond, that is non-polar. All right, and most everybody picked that. All right. Making comebacks. Which of the following molecules is polar? Consider the Lewis structure. Which one is polar? If you want to draw the Lewis structures out, go for it. But if you can imagine them, one of them is polar. Ten seconds. The correct answer is CH3Cl. A lot of you pick CO2. But why is CO2 not polar overall? Sure, carbon-oxygen bonds are polar, but you got symmetry. We've used CO2 as an example of a nonpolar molecule. Okay, the dipoles cancel out, nonpolar overall, okay? There we go. So next. All right. Here we go. Which of the following equations is not balanced correctly? This one's going to take a little more time. You got a minute and a half. So look closely. Bradley says this goes too fast. Yeah, and remember, you're not going to have a timer like this on the exam, but hopefully it simulates a little bit of kind of the pressures on. So one of these is not correct. Still got 35 seconds. All right, you got about 15 seconds. So at this point, if you're really not sure, just put an answer in. 5 seconds. Okay, everybody in. This last one. Okay, why is this one not right? Well, we've got here right here, potassium, 1 KCl, but you've got 4 chlorines and you got 4 potassiums on the product side. So you need a coefficient of 4 in front of this one. All the others should be correctly balanced. A lot of you picked the combustion reaction, but that one is actually balanced all the way through. Okay, Allie bumped Ashton. Let's keep going. We got 2 minutes left. Again, we may not get all the way done, but we'll see who's in the lead when we finish. Okay, we got this reaction. This reaction is best classified as what? Iron bromide, iron 3 bromide, and hydrogen sulfate makes iron sulfate and hydrogen bromide. Three, two, one. Should be double displacement, and pretty much everybody picked that. Good. 2 ionic compounds, cations, anions, switching. All right, we got time for like 1 or 2 more. And that's it. Okay, determine the molar mass of barium hydroxide. You need a calculator and a periodic table. Barium hydroxide. Yeah, if you got to go, head out. I get it. Thanks for joining. Barium hydroxide. You got barium, 2 oxygens, 2 hydrogens. Where do I find the recorded Zoom lectures? Claire on Blackboard. And if you click on online classroom, and then if you go into the lecture folder for 1050, you see everything sorted by chapter. This will be in the chapter 6 folder. I should have said what the mass of barium is, huh? Barium is 137. Barium is 137. That helps now that you have 5 seconds left, doesn't it? Okay, 171.34. If you Googled it, way to work smarter, not harder. Okay. All right, we're at 12:05, so this is it. This is all we have time for. So first 3 winners there. And I'm really sorry, numbers 4 and 5. You guys are so close. All right, so Allie, and then other Allie Spellman, and then Ashton. Why don't you guys shoot me an email if you're the first 3 and tell me how you want. What about the 28th spot, Bradley? Noble effort, okay? Please, in the game, I want to win. All right, well, hey, thanks for joining.